Just delighted to have Mike here to really give us a sense of how appropriate it was to think about the law as an operating system as someone who's thought very hard about the evolution of software. So Mike.
So my name is Mike Godfrey. If you want to follow me on Twitter, I'm MyGod. Hard to forget that. That really is me. And I'm a member of the Software Architecture Group, or SWAG, as we call it, at the University of Waterloo. One of the first questions I got last night, I've never met any of you before last night. This is a little daunting to me. I've never talked in front of a smart, general, and not computer science audience all at the same time before. Where is Waterloo? It's about an hour southwest of Toronto. You might have heard of a few of the things that come from there apart from the university. If you're a fan of ice hockey, Bauer Hockey Equipment came from there. If you're a fan of drinking, Seagram's was founded in Waterloo. And maybe in terms of technology, the thing you might have heard of is the BlackBerry, which was founded by people from our university basically across the parking lot from my office. So off we go. So I've got three things I want to talk about today, and they're all related. So first I wanted to talk about operating systems, and I know this is going to bore some of you and it's going to confuse others, and I'm sorry, but I've got to find some sort of level at which to attack this. Talk about what they are, how they've evolved through time, what are the services, what are the general observations in terms of design that we've noticed happening over time. I'd then like to generalize that to the notion of software evolution in general, not just operating systems, but large systems. And in particular, one of the pieces of my early work was on the evolution of the Linux kernel, and I'll talk about that in that section as well. And then finally, because we talked about evolution, I'd like to talk about how we got to designing software in the way we do now. That is the process of software development and how that has evolved over time as well. Because we write software in terms of processes very differently from how we did it 20 years ago. And that's affected, of course, the kinds of products that we're capable of producing. And I think it's been not only great for innovation, it's also been very good for reliability. So I know in biology they have a term, evolutionary development. That is how the process of how individuals develop over time rather than population evolves. So they call that evolutionary development. And I guess this is kind of the analog of that, how software development itself has evolved over time. So we'll set the Wayback Machine to about 1950. And off we go. Now, before we get into this, I need to interject a little bit about what operating systems are and how maybe they relate to the law and how maybe they're a little bit different. When we have a large software system, especially one that is concurrent, meaning it has resources, but it has a lot of different processes active at the same time, trying to share the resources in a reasonable way. Usually that's the system's job to mediate that, and that's basically what an operating system is. We talk about two kinds of properties about these systems that we care about deeply. Obviously, you can read the source code, but generally what we want to do is to have an idea of these abstract properties that we would like to be true of the executing system. And then we examine the source code to see if we think these properties hold. And we can use theorem provers if we're very adventurous, but more likely we're going to do simulation or we're going to do various kinds of testing. The two kinds of properties, the first kind is called a safety property. And you can think of this as no bad thing ever happens. So these are a list of things that you want to make sure can never arise in your operating system. So one example is something called deadlock. Deadlock happens when you have resources, you have processes using those resources, but they want more, and none of them are willing to give up what they have. And at that point, the system is deadlocked because nobody's willing to release what they have. No one can make any progress. So that's an important property of a concurrent system, that you shouldn't have that. And we can formalize that in terms of graph theory and logic, and we can do analysis of the code and try and work out that we're safe that way. Now, obviously, you want those safety properties there. But that's not all you want, because a brick, in the computing sense, is entirely safe because it doesn't do anything. So all of the safety properties hold, but it's not useful. So what we'd also like to talk about are liveness properties. Something good eventually happens. So that if you are if you do some set of things, then you're guaranteed at some point in the future the thing you wish to happen will happen. You may or may not have timing guarantees about it, but good things eventually happen based on an analysis of the code. So if the user presses confirm, eventually the sale is processed, their shipping is notified, their credit card is charged, etc. Now, I'm going to pause for a second. I'm not a lawyer. I have no legal training, not really much of a business person either. I'm a little bit of an amateur biologist, but only a little bit. So I thought, well, if I'm going to get involved in trying to compare these two things, I ought to, at least philosophically, have a view about what I think they are. So for me, and this is roughly stolen from the academic's best friend, Wikipedia, the law is a system of rules enforced through various social institutions to govern, that is to say, constrain behavior. That is, the law is mostly about making sure that bad things don't happen. It is not mostly about ensuring that good things do happen. That's left to you. Maybe the government has some social programs, etc. So what does the law have to say about parenting? It has things to say like, you shouldn't send your kids to the workhouse. You shouldn't beat them, that sort of thing. It doesn't say much about how much screen time you should give them, how much you should encourage them to go outdoors and play. That isn't the law. But those are maybe properties, liveness properties you would want to have for a program about parenting. So again, the law is mostly about safety properties. An operating system, while it has to have these safety properties, is mostly about providing services, taking advantage of the fact that it controls a bunch of resources and that there is a bunch of clients, applications, users sitting on top who have needs. And what it does is, in a reasonable way, and in a fair way, and in a safe way, tries to provide services that the people on top, the applications and the users, can make use of to get their jobs done. So fundamentally, it is about providing services, liveness, while at the same time, of course, you do need these safety properties. So that's my opening metaphor. So we get a little techie now. I'm sure everybody in the room has a laptop and has a vague idea of what an operating system is. But you can think of it as basically having two levels. It's got the kernel, which is where the really nitty-gritty scheduling and resource allocation, resource management happens. And it has a user interface. You don't interact directly with the kernel. The kernel provides a set of what are called system calls, which serve as the interface for clients. And the clients could be applications, or it could be the user interface of the operating system. So, for example, those of you who have Macs, I have a Mac, the kernel is actually a dialect of Unix. You may not know this, but if you open up Terminal, you actually get the Unix command line. It's Unix underneath, and then Finder and everything else, that is a layer written on top of that that makes use of the system calls to implement the user interface. So similarly with Android, those of you who have an Android phone, it's also Unix underneath. It's actually Linux, which is a different version of Unix from what Macintosh uses. And down below, you have a set of devices which have to be managed. You also have things like access to the file system and the scheduling of processes. If you have a single processor, a single CPU, and you have multiple applications running, they're not actually technically running at the same time. They're active at the same time, but they're doing time sharing or time slicing so that the CPU is allocating a little bit of itself to each of the active processes, partly based on what it thinks is the right, and partly based on what the demand is. So if we go back in history, the very first operating systems would have been written on the very first commercial computers, which we refer to as mainframes. Mainframes are still with us. Maybe the biggest, most interesting one in history is the IBM 360 and the operating system that was written on top of that, which was also called, well, was called OS 360. And that's mostly, you've got big iron, you've got a bunch of jobs that people want run. You have human operators generally who are doing the running around, making sure everything works. And it's not, I would say it's not very sophisticated, but it's getting the job done. The real revolution happens around 1970 when we get slightly smaller computers, which are still pretty powerful. And we have the operating system that really changed it all, and that is Unix, which was developed by Ken Thompson, Dennis Ritchie, Brian Kernighan, and a handful of other people, a relatively small number of people. at Bell Labs in Murray Hill, New Jersey. And this was a revolution. And as evidence to that, almost all operating systems that you use today, with the exception of those from Microsoft, have a Unix core. So that design, small, simple, elegant, and then when you combine it with the command line user interface, which would involve a lot of command line utilities, if you're familiar with that sort of working with a computer, and many people are not, the design philosophy there was small, simple tools that do one thing well, that have simple input and output, so you can string them together. And once you're good at that, the world is your oyster. Microcomputers, those are much smaller, much slower, much less memory, come around into the marketplace in the 1980s. And the very first operating systems, they were pretty stupid. CP/M and DOS were basically, load a file, execute the thing. It wasn't very sophisticated in user management. And the first versions of Microsoft Windows were basically lipstick on a pig. They weren't very interesting things in and of themselves, and they tended to crash a lot. The early Macintosh was a little bit slow relative to the computer it was running, the hardware it was running on top of. It took a very different philosophy. And then in the early 1990s, the first versions of Unix that were capable of running on these small, slow machines came into existence. One of them was Minix, done by Andy Tannenbaum, who's an American who lives in Amsterdam. And then there was Linus Torvalds, who is a student at University of Helsinki, who decided for fun just to implement something that was kind of like it, and it grew into the thing we now know as Linux. And later, when Steve Jobs rejoined Apple around 1999, one of his conditions was, we've got to get rid of the old operating system that was not Unix-based. We need something brand new that will run on these nice, fast chips. And I want it to be a dialect of Unix underneath, which was Next Step, which was the company he owned. And so that's why Macintosh is now, OS 10 anyway, is Unix underneath. And then we move into the era of the mobile devices. And those are, again, small, not necessarily slow, but there are only some kinds of things you could run on them that would work on a small device like that. Power management becomes an issue. And in every case, Palm Pilot and BlackBerry, their original operating systems were not Unix-based, but their later ones were. And Android and iOS are both, again, Unix underneath. So when we look at what's true of the marketplace today, while it's true that Windows holds dominance on the laptop and desktop, just about everything else is a Unix-based system at its kernel, at its core. And that includes things you might not realize, like the Kindle or PlayStation, for example. Those are actually Unixes underneath. Xbox is Windows underneath, as you might expect. So what have we noticed in terms of design about the evolution of operating systems? Well, we notice things like as new features come in, things in the hardware that we need to support, those of course get added in. So multi-core processes, concurrency is a whole level of pain different from non-concurrent and non-multiprocessor systems. You have to worry about scheduling and coordination a lot more. Power management, new kinds of devices, but sort of at a more fundamental level, the thing that we noticed was initially we were happy to have something that worked and was reasonably reliable. But then we wanted to start implementing different things. We wanted to be able to switch out ideas of which file system we used, what kind of devices we supported, and we wanted that to be mostly sort of plug and play, is the phrase we use now. So in the beginning, things were hard-coded. You would have a big operating system set of files where everything kind of knew about everything else. And they did what I call secret sharing. That is, you have an idea of the thing that you implement, and it's implemented in kind of a dirty way with pointers and addresses and nasty sideways things. And then you have an interface that sort of says, if you want this functionality, just press this button. Well, initially, there were no such buttons. Everybody knew everybody else's secret. And this made it very, very difficult to maintain these programs, much, much more complex. So what happened was, as we got confident that we would be able to afford the reduced efficiency of adding these abstractions, we started to recognize internal boundaries within the system that made sense. We created interfaces and we allowed things to be switched out. So abstraction, interfaces, virtualization, all these ideas are, I have an abstract idea of the thing that you want to know about. I'm not going to tell you very much about it, and you have to go through this interface if you want to use it. And then I can change my mind about the thing that's plugged in there. So there are many different implementations of file systems in Linux. The user doesn't need to know. I'm not even sure what's running on my Linux virtual machine. I think it's ext4. I don't need to know. It doesn't matter, and that's how beautiful it is. And finally, the idea, and this has been used on a number of open source projects, the idea if you want to have something that's interesting that adds new things on, try to make the core stable, don't muck around with the interfaces too much, and allow variation and experimentation and risky practices on the fringe, on the outside. So if you're trying to contribute to the Linux kernel consists of a bunch of code for dealing with the internals and also a bunch of device drivers for dealing with funny devices. If you want to commit something to the kernel itself, well, good luck with that. You need to be one of a very small number of people who are trusted to have that. If you want to commit a device driver, that's a lot easier because it's unlikely to mess around with the complexity and the correctness of the internal core. And another thing that happened, and this is kind of related, the idea of a monolithic kernel where everything's inside, and the idea of a microkernel arose. And what basically that does is it takes some of the fundamental functionality of the operating system and takes it above that into user space. And that makes it a little bit more efficient. It also makes it more complicated. It's been a mixed blessing. So Linux is a monolithic kernel with something called loadable modules. So what that allows you to do is to have things that are active during the execution, take them down and put new ones in their place. But it's still a monolithic kernel. With microkernels, a lot of the stuff is happening outside and it's harder to deal with if you're trying to figure out what's going on. And then finally, I wanted to bring up the idea, although I don't have a lot to say about them here, of software ecosystems. And this is increasingly an idea that's catching on in a lot of development communities. The idea here is not, well, there's a bunch of apps and they know each other, but rather there is a set of users focused on a particular kind of problem space or a particular programming language or a particular domain. And what people have done over time is develop these little widgets, these little infrastructure things that help each other out. So if you want to write something that runs on top of Linux, for example, and it has a graphical user interface, there's a lot of the widgets have been supplied already by either GNOME or KDE, depending on which religion you want to follow. And in addition to the user interface support, there's also a lot of little services that you can rely on. And these are not designed by some monolithic corporation or some group of people all sitting together in the same office. This is done cooperatively, and it's really fascinating to see how people get involved in a community like this and contribute voluntarily to make the community as a whole much more functional. So if you do statistical modeling these days, the R system is the place where you want to be, not because it does what you want, but because there are so many people in there, and the thing that you want to do has probably almost certainly been done more or less by somebody else, and you can take advantage of that in the stuff you're doing. So in the more general problem of software evolution, I'll tell you a little story. When I was a new academic, I went to a conference in Los Angeles in 1999, and I met a professor who was well known, but I had never met him before. His name was Manny Lehman from Imperial College in London. And he had written a lot about software evolution over the number of years that he'd been active. He had started out in the 1950s working at IBM while OS 360 was being developed, and he had a lot of experience there watching what was going on and drawing conclusions about it. And what he said was, well, you're probably familiar with the S-curve, or a logistics curve for things that are successful. You have successful, wildly successful growth in something. So the first person who brought rabbits into Australia brought a few dozen because he thought it would be fun to have rabbits to shoot at on his property. Well, there were no natural predators there apart from the occasional dingo, and there aren't that many of them, and the population exploded. But eventually, as tends to happen with all physical things, it tapers off because there's only so many rabbits that will fit into Australia, or there's only so much food they can have. And so that's why it tends to taper off. And he said, but that's not what's happening with software. I can show you a bunch of different commercial systems and how they've grown and how that growth is tapered off once it reaches a million lines or so. And he says, it's not we're running out of programmers or we're running out of ideas. It's the internal complexity of the system that is the problem. As it grows, there's a demand for more and more features. These get added. The core architecture is not redesigned. And eventually, people just spin their wheels to implement a simple feature involves knowledge of so much of the system, it's very, very hard to get anything done. So he says, and that's what's happening in most large software systems that are evolving. They're hitting this ceiling, and they can't go forward from there. And he also said, and you should read my paper on the laws of software evolution. I went, oh, okay, laws of software evolution. So don't try to read this. You can look at it later. It basically says, interesting software needs to grow, or people are going to stop caring about it. However, this growth means the system is more complicated, which means things get slower and slower and more unreliable, so you have to watch out. And finally, the last one is maybe the more interesting one, because it flies in the face of at least what academics said about software development. At the time, the important people who talked about software and programming and correctness were people like Tony Hoare and Edsger Dijkstra. These are Turing Award winners, very famous people. And the philosophy there seemed to be that, well, if you look at a program, a piece of software, it's basically a kind of algebra exercise. And you can prove properties of it. And if you can't, that's just because you're not a good mathematician. And you need to be a better mathematician, or your software is never going to work. So all software is a passive theorem, and the only thing standing between you and correctness is throwing it at a theorem prover or bashing it with your mathematical knowledge. And Lehman said that's strictly true, but it's not useful. He said the better way to think of this is more like an engineering system. You can understand the individual components fairly well, but you don't understand the way in which they're interacting with each other. And you don't understand on how things like the complexity of the system feeds back into development and changes the decisions that people make. Also, all these systems get deployed. They have a user community. They'll also have a software development community. They will all have cultures. All of those cultures will also impact how things get developed later on. So I asked him, I'm going to summarize. This is basically what I just talked to you. And so one of the key things he said was that growth is never going to be better than constant. You're not going to get this strong growth going on into millions of lines of code. It's going to taper off, and it's going to do that S-curve kind of thing. So at best, it's constant. And I asked him, have you looked at open source systems? Because I think they're developed pretty differently from all the systems you've looked at, which were commercially developed using old management techniques. And he said, well, no, but I'm sure it's all the same. And I went, okay, there's a research opportunity there. So anyway, his advice is manage complexity and do periodic redesigns. So in 2000, I downloaded 96 versions of the Linux kernel, which was a big deal in those days. I got into trouble with the network people at the university because they thought I was running a spam server or something. And I plotted the growth. And I plotted it in various ways. This happens to be a number of source files. You can also count lines of code and other ways. And it all is the same basic shape. And if you look at it, you go, well, that looks pretty much like it's better than linear. And if you do a little fit, and I'm not much of a statistician, so I went across to the stats department. They said, okay, well, this is how you figure out what a good fit to the line would be with a second-degree polynomial. So there we go. And I went and showed it to them. And I said, so this seems, your laws 3, 4, and 5, 4, 5, and 6 seem to be wrong. I've done a big analysis. The amount of work going in is not constant. The amount of effort is not constant. And it's still growing, and you said it shouldn't have been. I said, well, that's pretty interesting, so go back and do a little more work. So I did, and this is one of the first things I did was to kind of take it apart. When I got an electric razor when I was 16, the first thing I did was unscrew everything and then put it back together and noticed I had a part missing. Yeah, that was not a happy day. But I took this apart, and I looked at the source code in the decomposition of the files into directories. And so this is just the top level view. And these are the major subsystems as they were when they did the study in 2000. And the first thing you notice is that there's one big subsystem there that's way bigger. It starts out at about half the code, and it goes on to be about 63% of the code. And that one thing is called drivers. So these are small pieces of code meant to run a specific device. What does this mean for the complexity of the system? Device drivers are largely independent of each other. So however complex they are, that complexity is kind of limited to that particular driver. Some of the drivers are related to each other, so there's a little bit of shared complexity there. But mostly, they're kind of self-contained. And when they interact with the operating system, it's through a relatively narrow interface. So what that means is all the rest of the operating system, which has all of its complexity here, doesn't really need to know about most of the complexity over here. So something that looks very big maybe isn't quite as big as we think it is. If you look at Arch and FS, FS's file system, there are many, as I said, many implementations of file systems, but they all do the same thing. So the complexity there you can think of as having small bits of variation with each of the different philosophies. Sometimes they're larger, but they're not really fighting with each other. And again, they're interfacing with the rest of the system through this relatively narrow interface. So if there's one maybe takeaway of this whole talk, the one thing we've learned about software development is something a guy named David Parnas said years ago, and that is the idea of information hiding. And that's basically the idea of the interface. If you can figure out good interfaces, isolate the details from the essence of the thing, and have external people only depend on your interface, that's going to give you a robust design that's going to last you. And yeah, you have to redo it, but that's the key idea. Hide your secrets. Don't expose them. Figure out what the public face should be and expose that. So Arch is actually where the main kernel code is for each of the different chips that Linux runs on top of. So again, they all do the same thing, but the complexity really doesn't fight with each other. So this is how a very large system, if you compile it, is actually not as large as you think. So then I was trying to look at the kernel in as many different ways as I could. And so one of my things I wanted to know about is the design getting worse? One of the ways in which that could be true is if it was suffering from what we call interface bloat. That is, interfaces start having more and more things added onto them to the point where it's a big mess and someone should have rethought this. In the C language, what we typically do is we take the interfaces of the functions, which is basically one line per function, and we put them in what's called a .h file, and then we have the implementation in a .c file. Now that's convention, and usually it holds. So the idea that the size of the .h file, once you got rid of comments and other things that don't matter, should be a good measure of the size of the interface. And so if we looked at the average, we saw that yes, there was this fairly strong growth, growing from 60 to about 120 lines of code, which is a significant growth for this. But then, of course, you put on your statistician's hat and you say, well, the average doesn't tell you much. Look at the median. If you look at the median, it's pretty dead flat. So what do you know about a problem when the average is different from the median? Outliers. And in fact, there were only about 8 files out of a few thousand that were contributing to this growth. And what had happened was, in each of those cases, they had taken a very large data set and encoded that as explicit values in a struct, if you know what that is, and shoveled it in there. But what that meant is my underlying assumption that this was a good proxy for interface bloat wasn't right. So the moral is, when you're measuring something, make sure the thing you think you're measuring is a reasonable approximation to the thing that you are measuring. So just in terms of Linux, a couple of the phenomena that we noticed, and there's a bunch of evolutionary patterns from the community that we've developed over the years. One of the things we noticed is that because it was an open source system and was developed in the open, and because it was a competitor to Microsoft was trying to get everybody to buy Windows servers, And a lot of the industry did not want to be beholden to them, so they saw this as an open, viable alternative that everybody could share. So that seemed to be a big motivating factor to get a lot of companies like IBM and Sun and Hewlett-Packard and so on to start to contribute their own time and their own developers, paying their developers to work on open source systems, and their work would then be disseminated to the community. So they were working on stuff for the betterment of everybody else because it was in their own best interest to do so. Another thing we noticed, careful control of the core code, but allowing more flexibility on the fringe. Mostly parallel, and the idea of interfaces and virtualization, so you can plug in parts, enable sustained growth, allows you to change your mind over time. And something called clone and hack, which is usually considered to be a bad thing. There's something that you like out there that solves a job. Your job is similar to it, but a little bit different. So you just copy, paste, and change. And usually that's viewed as lazy development, but there are actually cases where that makes sense. And I've got 3 or 4 papers on that, but I don't really have time to go into them. And so finally, I want to talk about how the practice of software development has changed. And for those of you who don't know what that is, that's a rugby scrum. And rugby is unlike American football. What you have is everybody kind of mucked in and pushing and trying to move things down the field as a team. And that's a metaphor that one of the so-called agile developments uses, the metaphor of the scrum. Everybody is pushing. The other team isn't your competitor. The other team is unknown issues and complexity. So you're pushing against that as a team to try and get down the field towards the goal of a system that actually works. But let's back up a little bit. If you were writing code in the 1980s and you worked at IBM, you'd have to wear a jacket and tie. And this is how we tended to view software development. We viewed it as a progression, starting with the earliest thing, the earliest exercise. And you might have 8 or 10 of these. I've just made 3 here. And then you would finish that. So the requirements team would finish the requirements, throw it over to the wall to the design people, and then you get an architecture, you get a high-level design, and then you get implementation, and you'd be throwing them over the wall to the next team. And eventually you get down to testing. They would make sure it was worked according to how they understood the requirements to be, and then you do deployment. So this is called the waterfall model generally because the logical progression of the work goes in this direction, and it still does, even in approaches that don't follow this. But a key idea here is that you finish one activity, and then you throw it to the next people, and they keep going on. What happens in reality? This is what happens in reality. You get feedback. Sometimes people call this the salmon model because you discover things that you got wrong. You made mistakes or unreasonable assumptions about the requirements. You had to change your mind, and you had to force it back. And this model was not designed with the idea of, let's do something different or let's throw out this design decision. It waits until the last minute to implement stuff and then to test that that's what you want. And if it's totally wrong or totally impractical, you don't have a lot of help there. So we sometimes call this big design up front. It's really the old school engineering model, and it works well with a lot of old school engineering because the later stages there are what you might call more routine, more manufacturing. I don't want to do a disservice to engineering, but a lot of engineers will think that the design is the only important thing. And yes, you have to make accommodations as you go along, but you spend most of your time at the earlier stages trying to get that right. So throw it over the wall to the next people, change is expensive. You have hierarchical management rather than everybody mucking in. And you have this idea at the end of big bang integration. What that means is you hope you got the design right, you've allocated different modules to different teams, you hope they understood, and then you merge all of the products back in right at the end and hope that everybody understood everybody else. And that's why it's called big bang integration right at the end. And often you get nasty surprises. So what's the alternative to this? Well, many of these ideas date back to the 1970s. It's only been in the last 15 years or so that we've started to realize just how well they work. These days we use the term agile as not a specific methodology, but as a style of doing it. And you're doing basically the same things, but you're iterating back to the beginning. So instead of finishing the job of requirements engineering, you do a fair chunk of it, and then you prioritize how you could possibly build something that could implement some of the functionality. You build a few features, you test them, you evaluate them, how well did we do, then you go back. Okay, what are the next set of features that we want to implement? So this is an iterative model. Each time you're doing a little bit of requirements, a little bit of design, a little bit of testing. The earlier iterations feature more of the earlier, logically earlier work. So you're doing a lot of requirements in the early engineering, not so much at the end. You're doing a lot of testing, you're actually testing as you go along. You're doing a lot more routine programming at the end, not nearly so much at the beginning. So that's the idea there. Multiple iterations. Try to make the expensive decisions earlier, because those are the ones that get you into trouble, but you get the advantage of feedback. You've been working on this, you have an idea for how the architecture of the system might work, and then you realize early on after iteration 2, this is just not going to work, we need to have a different approach. So you're making use of feedback to improve the design. Get good at effecting change. To be a software system is to change. If we didn't change it, we'd just do it in hardware. The reason we do it in software is we want the flexibility. And since what we do is change, you should get good at making change, get good at effecting it. So each time we're doing a planning, an execution, an evaluation, and ideally a release. So at the end of each little iteration, you should, according to the methodology, at least in principle, have the ability to release a partial system that implements some of the requirements. But this is very different from the old system. Here, everybody's working on the core system from day one. When you're doing a contribution, you're not testing your little a module in a silo somewhere against the requirements somebody gets you. You're integrating them into the real system. You're building the system every evening, and you get a new version of it. You're committing your code to the common repository every day. So you have, instead of, I did my bit, and if it doesn't work, that's not my fault. Instead, if there's something wrong with it, it's everybody's fault. It's everybody's problem. We all share in the design, and we share in the decisions. And there isn't the big management from on high, delegating, delegating, delegating. Instead, you have a customer or a client who is a proxy for what should the system do. And most of the other people involved in it may have different levels of expertise, but they're all mucking in together. And although there is usually someone who sort of takes charge of the development, it isn't necessarily the boss or the most experienced person. It's the person who best understands how the various smaller steps of the process work and make sure everybody's doing the right things. Often these begin with a meeting where everybody talks about what they're working on, what they're about to work on, and if there's anything blocking them. And they hold these meetings standing up because it's uncomfortable. So you say what you want, and then you get to work. And these meetings take 15, 20 minutes maybe. And that's the key thing, just to have a communicate about the key things that you're doing and the things that are stopping you from getting your work done. All right, well, I'll just go on to talk a little bit about open source development. So Agile generally requires people on the same site, everybody working together, having some face time and talking to each other. Open source development can be done in a variety of ways. Often you'll have teams from different companies in different co-located parts, or you could have weekend programmers working on it. Good citizenship is very important, and because everything is done out in the open, everything is transparent. If you screw up, not only can your coworkers see it, everybody can see it because it's in GitHub, and everybody can watch what's going on in GitHub. Just finishing up, so repositories like GitHub have made the practice of software development much more visible and much more transparent. This has turned us into, I think, a much more conscientious community and is maybe something in some domains that we can learn from. So summing up, operating systems provide services to clients. That's fundamentally what they do. Most of the time, the design you don't get right, but after iterating, the right design reveals itself to you, and virtualization and interfaces allow you to move forward. Change is essential to software, and software changes are planned. This is not like how biological evolution happens, but even then software systems still exhibit emergent properties. So sometimes these are bad things like interface bloat, sometimes these are emergent uses, things in which you didn't realize that the software could be used for. And two things, emergent self-organizing development processes work too. So agile development is one style where everybody is on site, and open source in a more relaxed way where people may not be. But again, transparency is the key. And there we go.
Thank you for a very interesting talk. So I have a question about the development of the kernel of Linux. I know here on the last slide you had about self-organizing and not so hierarchical structures and hierarchical management. But then if you look at the actual process of the kernel, how Linux produces that, I mean, it seems like you have the different layers, and in the end, he's the one who pushes the pull request. And he's like a hierarchical figure in the top.
Certainly that's true now. That was much less true at the beginning. You know, famously he posted to Usenet saying, "Hey, anybody want to help work on this?" And the problem there was he was very, very popular. And so he had to figure out ways of managing, you know, the amount of stuff that was crossing his desk. So he became, in his own minds, a bit of a jerk, except he used a different word. And that's maybe sometimes what you have to do. And especially now that it's a very well-established thing, you don't have as much development happening in the core. You have more things happening around the outside. But if you go to work in a company that's practicing agile development, you do notice this happening quite a bit. So there are kind of two different styles, but they are, at least in the beginning, certainly less managed than the old way of making the big decisions. Now he's more in maintenance mode. Yep. 1, 2.
How much does the testing depend on the software you're developing having modular components?
Everyone's always agreed that testing is important, but like the weather, not everyone does very much about it. So if we've learned anything from agile practices, is that testing is maybe the most important thing you do. It ends up defining what correctness is for your systems. There's a philosophy called test-driven development that basically says, before you write code, write the tests, because then you'll know if the code is what you intend it to be. And if you discover a bug, that's a test you forgot to write.
But could you do it if it wasn't modular?
So where are the boundaries of testing? We generally do what's called unit testing, which would be at the level of, say, a file, and then files would collaborate to form a module, and so you might do testing at that level as well. So yes, so you get a hierarchical, as whatever you think the design of the system is, approach to testing as well. But you build the tests as you're developing in an agile way. You're building the tests as part of the source code of the system. It is not something in addition to the system. It is a core part of the system, the test suites. And so, yeah, if you are committing code, you're also committing tests, and those better work.
In one of your early slides, you mentioned the term security, but unless I missed it, you didn't mention it after that. How's that security stuff working out for us?
How's that security stuff? So I guess it depends on what your expectations are. And the same goes with safety critical systems. The more it matters, the slower you go and the more careful you are and the more likely you are to use something that is in wide use and has been examined by, to use Linus's phrase, a bunch of eyeballs. Given enough eyeballs, all bugs are shallow. I'm not a security person, but I think the best way to ensure security is, except for maybe details of encryption, to make the design of these systems as open as possible so that there's a lot of people who can scrutinize them. That seems to be a much better way than the phrase we use, security by obscurity. I keep everything secret and hope that I don't get a disgruntled employee who figures out there's a back door there. 1, 2, and then I'll go to this side of the room.
Thank you. A couple of thoughts on the potential relevance of operating systems to law. The first, just a reaction to something that you said early in the presentation, where you said law was mostly about constraining behavior. I don't agree with that. I think a lot of law is about enabling coordination and cooperation and sharing resources. So what makes an enforceable contract? What makes an enforceable will? What makes an enforceable marriage? Who gets the assets of an insolvent debtor? How do shareholders elect the managers of a company?
Okay.
And so there's lots and lots of who pays for accidents and mistakes.
Right.
So there's lots and lots of law that's not about constraining behavior, but that's about how we coordinate and share resources, which sounds a little bit like what you were describing one of the main jobs of the operating system is. The second thing that struck me is when you were talking about agile development. It made me think about some properties of legal evolution or attributes of how laws come into existence. And in particular, the concept of principles versus rules. And when you have a principle, the actual rules kind of get worked out over time, iteratively. And when you have a rule, well, the rule's the rule. And there's not exactly the same, but maybe a similar concept or a potential analogy in the common law versus statutory law.
Right.
So in the common law, the principles and the rules get worked out over time by judges, whereas statutory law, they get written down once by a legislature. So I think there might be a lot of analogies here that seemed interesting to me.
So I guess part of the reason I put that in is so someone like you would tell me how I'm wrong. So I thank you, and I am so educated. But if I hadn't put that in, I wouldn't. So 1, 2. Oh, sorry. I saw a hand in a hand, and now I see another hand.
Okay, quick. What's the relative status of formal mathematical testing versus test case testing when the systems are getting really big?
Theory of practice, you mean what's the theory versus practice of testing with big systems?
Not so much a theory, but to what degree are we does the mathematical proving of correct software actually happen when we're developing a big system?
Short answer, not much. There are cases where that's done. Formal methods and formal proofs of correctness were a great way to get money from the Department of Defense in the 1980s, less so now, and broadly throughout the world. It had a lot of promise, or maybe a lot of promises were made. It didn't pan out. So instead what's happening is people are taking cases where there's a possibility that if you do this in this way, you could get real value out of it. So a good example of that would be model checking. And what you do with model checking is you have an idea of, say, safety properties you want to make sure don't happen. You create a model of the actual program based on your understanding of it, and then you basically bash it to death with enough cases to see if you can find any mistakes in it. So that's actually been very successful and has been used in avionics software, for example. But most testing is more driven by engineering than by math, an understanding of where the weak spots are likely to be and what they're likely to be. So 1, 2.
I've been struggling with this analogy between law and OS. And we've heard a little bit about the law, and the issue, I think, is sclerosis in the system, that everything gets kind of clogged up because of the complexity in the law. It's sort of like back to the old pointer system of developing software in law. An analogy might be that what we really need is an immune system, where we need T cells and B cells. We need something that actively goes out and fixes stuff in the law. Now, when we talk about the software, the OS, you talked about the kernel, you talked about safety, so you talked at a very low level of having things that would keep things safe. But I'm wondering if maybe the analogy for OS is we need something like a cleanup module. It's a slightly higher level because, we need things that, there was a comment last night about reevaluation of the results afterwards. Or maybe you need sunset provisions in laws so that we have some methods to clean things up. The only analogy I've heard in OS, maybe it's Amazon or someone who's working on sort of system-wide things that go through and look for bugs in some kind of automated AI method. Is that the level of how we think of an OS cleanup, or how do we do that applied to law?
Okay, so I'm not sure about the law, but let me tell you about computers. There is an area of work which we call self-healing and adaptive systems. and it's not so much a small operating system, but more, you know, a bunch of servers all cooperating, or a big IT infrastructure, something goes wrong. You have a little daemon, a little monitoring thing that's looking for problems, and when it notices something is wrong that it knows it can fix. Like say one of the what's the word? When you're trying to do network lookup. The computer that tells you where the network, what does the network mapping. Yeah. If one of those goes down, it will say, oh, I'll just bring another one back up here, and oh, now it's back up again. So IBM is a buzzword for it. They call it autonomic computing, and they make the metaphor to the autonomic system and autonomic systems within the body of doing healing when it notices something that's going on. So the crawling around looking for bugs, sure, you can do that, but I do think people are thinking of bigger systems and systems of systems, as we sometimes call it, with a view to what could we diagnose and how could we fix it if it's a reasonable thing to do in this case. So there.
So this was a fascinating conversation, and you focused very much on the technical characteristics of Unix that made it possible. But I think in a way to connect the question of what law is or isn't, there's an institutional innovation of the GPL and free software licensing that flips the standard idea of intellectual property and intellectual property protection, and it's that legal affordance that allows people to cooperate without thinking that the other side will, without disabling the possibility of the other side that's contributing, absconding with the code, was a critical invention.
Right.
And that's Stallman without the organizational innovation. The organizational innovation then is Linux, which is release early, release often, all bugs are shallow, and the model of open organizational innovation. That relates to your point about Scrum and Agile, which itself is part of a longer intellectual history of lean manufacturing coming out of Toyota Production System. So it's a moment at which the technical characteristics of the system you're describing for Unix intersect with legal inventions of the GPL and open source licensing, and then with organizational attitudes that you see far beyond just software of open network flows of innovation and knowledge, whether it's in studies of regions, whether it's in studies of Toyota Production System and lean manufacture, or whether it's software.
Okay, go ahead.
Just the critical thing for us, I think, in law is to recognize how that broad range of changes is part of an intellectual flip that requires that we rethink the idea of well-defined rights around self-interested motivations and appropriation rather than around shared exploration of opportunity spaces and worrying less about the appropriation part.
Right. So I should have talked about licensing, I think. I think that's a fair point to make. So if you have an open source system, it has a license. And the license, depending on the version, basically says you can download this, you can look at it, you can build it, you can play with it, you can even hack at it and do other stuff with it. But if you create something interesting, a derived work, then and make it available, you have to take your new thing and make it available under that same license. So the GNU public license, the GPL, done by Richard Stallman and other people, the Free Software Foundation. If you ever get a chance to meet Richard Stallman, he's an interesting character, to say the least. They sometimes call that the GPL virus, because once you've used a piece of GPL code, if you take some really nice library, depending on the specifics of the license, it may compel you to release whatever system you're working on also under the GPL. There are variations on the GPL and other open source licenses about how free you are, but it did have the intended side effect, and this was Stallman's strong idea. He wanted, you know, sort of a socialist utopia where all software was free, and that's not an exaggeration. And he saw the best way to do that was to create awesome software, which he did, and then enforce it that if you make awesome software, you also have to contribute it to the world. I think there was maybe one or two others. Maybe I can ask. All right, I have two pointers, so that must be a good question.
Thanks. The question comes from your title. I was expecting to see dendrograms, tree diagrams. So biologists have gotten a lot of mileage out of software, which isn't any harder to use than whatever you ran your regression on, which can array a group of genes or entire organisms' genomes in a tree-like structure where you can infer parentage and distance and evolutionary time. And so what's up with that, and why aren't you using it? And where others have used it, what are the critiques?
I actually have a whole body of work about recognizing duplicated code, which is, you can use a variety of techniques to do this. It's not just doing sequence analysis. You can also compare them structurally. I had to draw the line somewhere. So that's a different talk.
So I think a lot of what you describe has to do with the modularity of the software system,
Sure.
where the kernel, the tight interfaces and so on, and we know that allows for innovation. I think maybe an analogy in the legal system is, for example, the Constitution is our kernel. So constitutional is actually, we talk about how it all gets the sclerosis of a lot of our legal systems, but the US Constitution at the very least has been very adaptive and stable. So one question I have about the computer systems is, at what point will the kernel no longer play that role of providing enough freedom for the modules to evolve, enough capability, and enough of that sort of stability? At what point will the source of the evolvability in that system become compromised? And is there then an analogy with the broader legal system that can be drawn in terms of the vulnerability of the system?
So as long as you have hardware, you need a system that deals with the hardware and make sure that things are done in a fair way. In terms of what services you want to be at that level and what services you want to be above, that's the microkernel versus monolithic kernel argument. And it's complicated. But you're always going to need operating systems. The thing we're noticing more and more is that people are building systems out of components that are not on computers in their office. They're in Seattle or somewhere else, and they're not really sure how they work, but they know how the services work, and that's enough for them to get their job done. So everything is suddenly not just in the cloud, but is so virtualized we don't really know where things are coming from, and as long as they're reliable and they work, then we're good. So that's been one of the key technical shifts in computing. Is it's not one big thing that you built. It is a set of things you asked for and they got granted because you're plugged into this awesome network of services.
Follow-up on the same question is that, if this is a laboratory, and this is a great talk because I understand everything about it from being a computer scientist, is, the operating system I would come back to and say, yeah, is that the Constitution? And we've got to get at the right logical level, because if you get up into the application layer of the system, it's wild there, right? I mean, it's the Wild West with respect to applications now that are on the web, et cetera, et cetera. So we got to get at the right logical layer of where the law fits. So is it really true that, because when you talk about the kernel, I can, and you show your correlations, of course we want to drive the lines of code down. I mean, the biggest problem with software development is what you're saying there. So the kernel is an interface to the hardware. It's in some sense it's a simple problem that has been beaten on for 30 years, and we want to get it down. But where we see the explosion in innovation is at the wildest levels.
On the fringes.
On the fringes, and a lot of so I guess the question I'm just bringing is that we got to get at the right logical level, because the kernel is very restrictive. I mean, it's very restrictive, and those interfaces are very hard. So I'm not sure. I get the concept here, but I'm not sure. One of the questions I've got to get or want to understand is at what logical level are we talking about a software operating system, because applications are wild and they are at the fringes.
Sure. So in addition to we don't want to necessarily buy into Microsoft argument, another argument for supporting open source operating systems and web servers like Apache was we'd like to solve this insofar as we're able to in a way that we understand it so we don't have to worry about it again. We're sick of writing operating systems and web servers. These are very low-level things. We'd like to, we can't, but we'd like to, just nail them down so that we can go and do crazy wild stuff outside, because that's where the value is, that's where the innovation is. So, companies think, can't we just settle on this? Can't we just fix operating systems? And if you notice, people have used Unix because it works. It's a reasonably good philosophy, and that's why it's so popular. It kind of solves it in a vague sense.
But people incorporate in Delaware because there's large case law there. So in some sense that we make these decisions already in that we've chosen Delaware as a place to incorporate because of case law, right? You're a fool not to do your, that's one of the reasons. There's other reasons that are less, there's not transparency there. So I guess I'm trying to get at that. I'm not sure, we've made those decisions already with respect to law on the simplification.
Okay.
Let's take 2 more questions quickly.
1, 2.
Okay.
Come back to the question about how does this relate to law, and I want to really emphasize your point. You're talking about ecosystems, and you described a process that fundamentally emerged out of an open, this wasn't within a single organization.
Right.
This was not the world controlled by Microsoft or the internet controlled by IBM, which we could have had,
right.
But for some law, antitrust law. And I think that's where we have to think about where the problem we're running into in laws, which I think is developing in the way that Gary was mentioning here. And that is that we have a phenomenally closed system. We're not recruiting the benefits of multiple different types of entities thinking about how to solve these problems, compete these problems. We have it within a very closed system. Lawyers can provide legal services, governments make rules. That's a very closed system, and it's something that's only been around for a couple of 100 years. So I think that's what I'm taking away from ecosystems, is the crossing over of multiple entities, recruiting the importance of diversity, and multiple nodes of decision-making, problem-solving.
Right, so with these ecosystems, you also have sort of a technological entry barrier, that the people who would be annoying if they were sending mail to Linus, they're not there because they're not suggesting anything concrete. So you've got technically very able people making good suggestions, and if they're not so good, then maybe they don't get asked to contribute. So they do this in sort of a peer-reviewed kind of way, but not in an academic peer-review way. Oh boy, not like that. Yes?
To your point about how improvements in hardware make software below tolerable and manageable, and the question of what's the analog between operating systems and the law, I wonder if the counterpart to hardware is improvements in technology. FedEx, email make the US Postal Service tolerable and manageable. Uber and other ride-sharing services make conventional taxi cab services tolerable, manageable. George Gilder says that the progress of mankind is an arms race between growing regulation and technological innovation. A thought.
Wow. See, I think of the world as cooperative. I'm more in the ecosystem mode of, what are the things we can do to get a little bit further down the road of making things work better for everyone? So in terms of technology, the law is about a lot of things, and an awful lot of it is not technology. So I think we're missing out on a huge chunk of the world there. It doesn't say much about our relationships. It doesn't necessarily say much about how we run our businesses unless we're in the technology business. So I'm not quite sure I got the question.
Well, it wasn't so much a question as a comment.
Oh, so I don't have to answer. Okay.
Thank you very much, Mike.
All right. Cheers.